Last time, or this chapter, we've been talking about probability distributions, right? Last time we talked about a discrete probability distribution, specifically the binomial distribution. Today we're going to look at continuous probability distributions featuring the normal distribution. So that's our plan here. So when we talk about a continuous probability distribution, since it's continuous, we could plot all the points and create what's called a density curve. So in a density curve, we have a couple of properties. It's always above the x-axis, and the area underneath that probability curve always has to equal 1. And since we're talking about the probability of something, like the area under the curve is going to correspond to our probabilities, and since the total area underneath the curve is 1, we know then that's going to make like a probability distribution, right? So that's the idea. So say we had a histogram that looked at some 7th grade test scores, and if we notice, we can kind of plot a function that kind of goes over top of it. That function there would be a probability curve, since the height at the given x value is like the same as the height of the bar, right? So that's the idea. If I have a probability density curve, let's just review the mean and median, where those locations would be. So the median is going to divide the curve's area in half. And the mean would be like the balance point. So if the curve was like built out of something solid and you're trying to balance it on a point, the mean would be where that thing would balance at. Now, if our curve is symmetric, remember that the mean and median and really mode are all going to be located in the same location. So just as a picture, here's a symmetric curve. Mean and median the same location. Here we're skewed to the right because the tail goes to the right, which means the median is going to be here, about half the area is here and the other half is there. The mean is going to be pulled towards the direction of the skew. So the mean will be to the right of the median if our curve is skewed right. So this is still just a review of things we've talked about before. So the next thing we'll talk about is measures of spread, specifically the standard deviation. So one special type of probability curves or density curves are these normal curves that correspond to a normal distribution. So some facts about a normal distribution. All these normal curves have the same shape. They're all going to be this kind of bell shape, symmetric, single-peaked curves. And specifically, I can define any normal curve just with two numbers. I need to know the mean and I need to know the standard deviation. Using just those two numbers, I can construct any normal curve. So again, the center of our normal curve is going to be the mean, and the standard deviation is going to be the distance from the center to the change in curvature points on either side. So if we abbreviate our normal distribution, we would say x is normally distributed with a mean of mu and a standard deviation of sigma. Normal distributions are quite important in statistics, so they're good descriptors of many real-world data sets, and they can serve as good approximations for different situations that have chance outcomes. And a lot of our inference, so like making a prediction, is based on these normal distributions. So very important rule for normal distributions. This is something that you would want to have memorized. That would be the 68, 95, 99 rule. What that is saying is that if I have a normal curve where the mean is mu, so that's going to be 0 in this case because it's the center, and the standard deviation of sigma, in this case the standard deviation is 1, 68% of the area under the curve, or percent of our data, lies within 1 standard deviation of the mean. 95% of our data lies within 2 standard deviations of the mean. And 99.7% of our data lies within 3 standard deviations of the mean. So, question for you, how much area is there in one of these kind of middle blue sections here that I'm tracing over? How much is that? Well, you're close. It's half of that, 13.5. So the difference between 95 and 68 is 27. So this area and this area have to be 27%. So just one of them is going to be 13.5. Does that feel okay? Similarly, how much is going to be here in this darker blue section? .35 is correct. Yep, that's 99.7 minus 95 divided by 2. And then how much has to be way out here, this little tiny sliver? Half a 0.3, 0.15, right? Because I know the total area is 1. Everybody cool? How I figured that out? There will be some problems that we'll ask you to do where we won't give you enough information to get it into your calculator to do anything with, and you're going to have to use this 68, 95, 99 rule. All right. Let's talk about how changing mean and standard deviation affects the picture, the probability curve, the normal curve. So I have 3 normal distributions. The first one has mean of 5, the second one has mean of 10, and the third has mean of 15, but they all have the same standard deviation of 2. So if I graph them, this is what it looks like. What do you notice? All have the exact same shape. What's different, though? Their location, right? So the green curve is centered at 5. The red curve is centered at 10, and the blue curve is centered at 15. So what can we say about the mean for our standard, or for our normal curve? What can I say about the mean? It controls the location, right? And what's going to control the shape then? Standard deviation. Okay. So let's do the same thing now. We have 3 normal distributions, all with a mean of 5, but the standard deviations are 1, 2, and 3 respectively. So let's look at the graph of these guys. What do you notice about the shapes here? They're different. So notice when the standard deviation is 1, we got tall and skinny. Standard deviation turns to 2, we're a little bit shorter, a little bit wider. Standard deviation changes to 3, we are the shortest and the widest. Everybody feels okay about how the shape of a normal curve is going to be affected by its standard deviation? The bigger the standard deviation, basically the shorter and wider it is. What do I know about the area under all 3 of these curves? It is equal to 1. Okay, the area under any probability density function is going to be 1. Everybody feel okay? Okay. So let's say we have a group of students and we're asked to pick a number between -10 to +10. Suppose we found that the number of, or found the choice of the number was a normal distribution. If you wanted to figure out the probability that some random student selected a number less than 5, so the probability x is less than 5, I could draw a picture of my normal distribution and then shade the area under the curve that's less than 5, so this spot in blue, and then I could try to calculate this area, right? That'll give me the same as the probability. Now, to actually calculate that area is not trivial. We need to use we would need to use calculus to do it. In fact, calculus that's well beyond the scope of this class. What are we going to do instead? Use the calculator. The calculator will do this for us. Okay. Worth noting before we move on, if I have a continuous distribution, like a normal distribution, the probability that x is equal to a fixed value, to a single value, is always going to be 0. If probability means the area under the curve, if I have x equals 5 and I shade the area under the curve where x is equal to 5, it's just a straight line, right? If you remember from geometry, lines have area 0 because they are one-dimensional objects. One-dimensional objects have no area. So if you're dealing with a continuous distribution like the normal, the probability that x is less than 5 is the same as the probability that x is less than or equal to 5, because the presence of 5 has probability 0, so it include it or don't, it doesn't matter. Is that the same case with discrete distributions? No. Okay? Very important that you're checking to ask yourself, is this discrete or continuous? Because the way I treat that less than or equal to is very different. Okay? So what I point out here is that, again, these four probabilities are all the same, whether they're less thans or less than or equal to's, it does not matter, as long as our distribution is continuous. If we're dealing with a binomial distribution, these would all have different answers. Okay? Does everybody feel okay there? Okay. Going back, if we want to talk about percentiles, remember we talked about this earlier this semester. So let's say Jenny got an 86 on her test. How did she perform relative to the rest of her class? Well, if I count up Jenny's class, she scored better than 21 of the 25 students. So her percentile rank would be 21 out of 25, or 84%. This is the same thing that we're doing when we calculate the probability that like x is less than 5. Is the same idea as a percentile rank, right? Right, this would be the same value, this 84% would be the same as the probability that a student scored less than 86 on their test. Everybody kind of see the relationship here between percentile ranks and these probabilities, that they are in fact really doing the same, counting the same thing. Now, what will often happen is that you'll want to compare two measurements. Now, if you're talking about, like, let's say we have a boy and a girl, and they're both 5 feet 10 inches tall. And we want to talk about how really tall, is this a tall girl or a tall boy, when they're the same height, right? What does tall mean? Well, it should probably mean have something to do with their percentile rank given their gender, right? So what we'll do is we'll do something called a standardization process, or calculate something called a z-score. So to calculate a z-score, we take our measurement and we subtract it, or subtract the mean from it, and then divide by the standard deviation. That'll give you a scaled score relative to your population. So if we take our 5'10" boy, we take his height, divide it by the mean height for boys, and divide that by the standard deviation for boys' heights, we'll get a number. If we do the same thing for girls, subtract the 5'10" girl height from the mean height for girls and standard deviation for girls' heights, we'll get a number. Those scaled z-scores are now relative to the same situation. So we can compare those to say, okay, who is really taller than who? Does that make sense? For example, if you took the ACT one year and your friend took the ACT the next year, and you can ask who did better. Well, the average score one year is maybe different than the average score the next year, so you should scale it relative to the conditions in which they took the test, right? So that's what this idea is. Now, if we take a normal data set and we take every data point in our normal distribution and we convert those measurements to z-scores, we're going to get something very special called a standard normal distribution. We'll talk about that in a second. So if we go back to our old friend Jenny here, the class average for her test was 80 and the standard deviation was 607. So if we take the z-score for her test, she would have gotten about a 1. What that translates to is she scored about 1 standard deviation better than average. So if you remember our 68, 95, 99 rule, she'd be about the 84th percentile, because half of it is 50% and then the other half of the 68 is 34. 50 plus 34 is 84, which is the same thing we observed when we did the percentile rank from before. So this is what I was saying. If I take a normal distribution and I convert all of its all of its measurements into z-scores, we get something called a standard normal distribution. Oops. Go back. So if I take every score or every measurement in my distribution, I subtract the mean from it, what is the new mean going to be? Zero, right? Remember when we subtract a value from our data set, like if we had a bunch of temperatures and we converted them from Celsius to Kelvin by adding 273 to it, right? That's something we could do. That's going to shift the mean from the old mean and add 273 to it, correct? If I take every measurement and I subtract the mean for that data set, the new mean is going to be 0 because it's shifted from like 15. If I subtract 15 from everything, the new mean is going to be 0. What's the standard deviation going to become if we divide every measurement by the standard deviation? It's going to turn into 1, right? If the standard deviation was 5, or if I had like a bunch of heights in meters and I want to convert those to feet, and I multiply by, well, let's say we have a bunch of measurements in yards and I want to convert them to feet. I multiply by 3, I would expect the standard deviation to change by a factor of 3, right? The same idea here. So when I have a standard normal distribution, that's what I call it when I take every measurement in my data set and I convert it to a z-score, I get a normal distribution with a mean of 0 and a standard deviation of 1. Okay. All right, so let's talk about now how we use our calculator to compute some of these probabilities with a normal distribution. If you have your calculator with you, I invite you to take it out to follow along. If you don't have a calculator with you, you'd like to borrow one to follow along, I have 4 lovely calculators sitting right here for you. You're welcome to them. Here we go. We're going to just check the distribution, figure out what kind of distribution we have. If it's a normal distribution, we're going to draw the normal curve for it. We're going to label the axes with the mean and the standard deviations. We're going to draw the boundary values and then shade the area of interest. And then we're going to use our calculator. We're always going to be using normal CDF, okay, to answer the question. So let's say we have our random variable is related to the normal distribution 0, 1. What do we call this kind of normal distribution where the mean is 0 and the standard deviation is 1? We call it standard normal distribution. Really important that you know that vocab because they might hide that the mean is 0 and the standard deviation is 1 by just saying you have a standard normal distribution and not write it down. Okay, so I'll start by drawing my picture. So here's my picture, my normal curve. The center is at the mean, which is 0. And then I'm going to draw 3 tick marks and label them as with the standard deviation as my unit. So since my standard deviation is 1, my tick marks are all going up or down by 1 unit. I'm going to draw a boundary line at -2 and a boundary line at +1 and shade the area in between. So that's the area I'm searching for. If I want to do this with my calculator, then I'm going to press second and the vars button to where all the distributions live. I'm going to pick from that list, I think it's option 2, which is normal CDF. The lower is going to be -2. The upper is +1. And the mean is 0 and the standard deviation is 1. And then I'll press enter. And I get about 0.189 or about 81.9%, if you want to write it that way. So far, so good? Just like the binomial, right? Very similar. What if I do z is less than 1? So again, I'll start by same standard normal curve. So I'll draw my curve. So if I draw the boundary value, here's 1, and because it's less than, I'm going to shade to the left. Okay, let's go and enter this into my calculator. Uh-oh, the lower is, this goes on forever to -infinity, right? So when I type it in, I can't type -infinity into my calculator. So what I'm just going to do is type the smallest number that my calculator can hold, which is -1 times 10 to the 99th. That'll serve as my proxy for -infinity. To get that times 10 to the negative, or times 10 to the power button, that little E, you press second and the comma. That's where that E means for, or what that, how to get that E for scientific notation. If I do that, then it comes out to be about 0.841 or about 84.1%. So far, so good? What if I do z is greater than -1.5? Okay, again, we're still dealing with the same standard normal curve. So I'll start by drawing that and labeling it. I'll put my boundary line at -1.5, but this time I'm shading to the right. The upper for that is going to be +infinity because it's going on forever. So into my calculator, I'm going to do the same thing, but the upper, I'm going to input the largest number my calculator can hold. That's +1 times 10 to the 99th. And if I compute that, I get about 0.99 or 0.933 or about 93.3%. So far, so good. probability that z is less than 0. So I'll start by drawing my picture. And I'll go, wait a second! I don't even need a calculator to do this. I'll throw my calculator to the side. What does this probability have to be? 0.5, right? Why is it 0.5? Just half the curve, right? The curve's symmetric. The total area under it is 1. Half of 1 is 0.5. Ah! Wonderful. I did it with no calculator needed. So far, so good. What if I say the probability that the absolute value of z is greater than 8, or 0.8, excuse me. Ooh. So if I go then draw this, that means that things like 0.9, 1, 1.1, etc. would all be included. But so would things like negative 0.9, negative 0.1, negative 0.1.1, but nothing in the middle. So how am I going to do this? It's not connected, Mr. Kulik. So 2 different ways I could approach this. I could figure out one end of this and then multiply it by 2 because they're symmetric. Or what I would prefer to do, what if I just calculate the white region and subtract 1? Or subtract it from 1, I should say. That's what I would do. So I'm just going to go from negative 0.8 to positive 0.8 and then do 1 minus that number. Yes? Sure. Does that feel okay? All right. So what if I don't have a standard normal curve? Does anything really change? Not really. I'm still going to do it the same way. I'm just going to now have to make sure I'm being careful about inputting my, mean and standard deviation. So this is a little aside here. When I was in a high school student and we had to do this, every normal distribution, we converted to a standard normal distribution because we didn't have a calculator that could do this. How this worked when I was a student is you had a table in the back of your textbook of, like for the standard normal distribution, and you had to look that stuff up off the table, which stunk. So the old way of doing this would have been to okay, I'm going to take that 9.1 and that 10.3, and I'm going to standardize those, calculating z-scores. And the answer, or the question I really would answer would be this one. From the table, I'd have to look at the probability that z is less than 0.15, and then subtract from that probability the probability that z is greater than negative 0.45. And that's what I would have to do. But we don't have to do that anymore. So you could do that. These will both give you the same answer, whether you're doing the probability of 9.1 less than x less than 10.3 for this normal distribution, or if you do the probability of negative 0.45 less than z less than 0.15 for a standard normal distribution. They will both give you the same answer. It's up to you what you want to do. I don't know why you wouldn't just do this because your calculator can do it directly without having to calculate a z-score. So really, we're just going to do this. So I've sketched in my graph. I've drawn in my boundary lines. I shade my area. Why? Whoa, Mr. Kulik, these numbers are way different than what we did before. Why are these numbers so different? Yeah, remember the mean is 10, so that should be the center. My standard deviation is 2, so each tick mark should be 2 units apart. Everybody's good with that? So I enter into my calculator, upper, lower, new. I have to make sure I do the mean and standard deviation. Common mistake, students putting in 2 squared here for the standard deviation instead of 2. So when we describe the standard or the normal distribution, it's mean and then variance. So make sure that you're taking the square root of that number to get the standard deviation when you're typing in your calculator. Anyways, I punch that through and I get about 0.233. No big deal though, right? Let's look at some story problems. Oh no! Words. Eggs laid by a chicken are known to have a mass normally distributed with a mean of 55 grams and a standard deviation of 2.5 grams. Was the probability that A, an egg weighs more than 59 grams? So here's my sketch. So again, the mean is 55, and we're going up by 2.5s. So 59 is about here, and I want more than, so I shade this side. Use my calculator. 59 to positive infinity. Mean and standard deviation. Bingo, bungo, button push, and we're done. So far, so good. Okay. What about the probability the egg is smaller than 53 grams? Well, same idea. Sketch my picture, pull out my calculator. This time I'm going negative infinity to 53 with my mean and standard deviation. Punch that through about 0.212. What if the egg is between 52 and 54 grams? Okay, I'll sketch my new picture. That looks like that. Plug that into my calculator, 52 to 54, mean and standard deviation. I get about 0.230. Everybody's okay? All right. What if I want instead, what if I know the probability and I want to retrieve the measurement? Okay, what if I'm told the probability that X is less than some value is 45%, and I want to retrieve what that value is? Our calculator can do this. So we're going to be using as the inverse norm function. I think that's 3 in that distributions menu. So your inputs are going to include the cumulative proportion, which is just the probability, and then the mean and standard deviation. One thing though, inverse norm can only solve for X when X is less than blank. It can only do less thans. Well, Mr. Kulik, what if I have a greater than, or what if I have it in between two values? We'll show you how to deal with it in a second. All right. Again, make sure that when you're entering in that probability, it has to be as a decimal, no percentages. So 0.9 rather than 90%. Okay. So we're told that we have a standard normal distribution. And we want to find the value of A such that Z less than A has a probability of 0.877. So I'm going to draw my picture. So I drew this and I labeled. Now, I don't really know where this is at. I'm just kind of taking a guess as to what looks like about 87% of my area. Just kind of eyeballing it. There's no way to kind of figure that out without actually doing the math first. So I'm going to pick inverse norm, enter in the area under the curve with the mean and standard deviation, press enter, and I get 1.1, which is right about where I drew that. It's almost like I found the answer first and then drew the picture so it would match. I didn't do that though. That was a pure guess. What if I have the probability Z is greater than A equals 0.2? Can inverse norm do this as it's currently written? No. Has to be a less than. What am I going to do to fix this to get it into the calculator? I'm going to do the complement rule. What's the complement of Z greater than A? Z is less than or equal to A. What do I have to do to the probability if I do the complement? I have to subtract it from 1. So I'm just going to turn this into z is less than a equals 0.8. Now, why did I dump the or equal to? Because a normal distribution is continuous. Probability z less than a is the same as the probability that z is less than or equal to a. Everybody's okay with that? Remember we talked about that earlier? So I can always do that if I'm dealing with a normal distribution. So that's what's going into my calculator. And then kablamo! 0.842 is my measurement for A. Does that feel okay? What if I want to find the A where between these two values it's 0.42? This one's the trickiest, one of the trickier situations. The picture really helps me here though. So I'm going to start by kind of doing that. So we're going to do this. So what can I say for this part of the blue right here? What's the probability that we land in here? Between this boundary and 0. It's half of that, right? 0.21. And over here, it's also 0.21, right? So what I'm going to do then is I'm going to calculate the probability that z is less than a. Well, yeah. And to do that, I can just take this 0.21 and add 0.5 to it because that's half, right? So I take the half and add 0.21, and that's going to be 0.71. So the probability that z is less than a is 0.71, and now I have a problem my calculator can do. Is everybody okay with what I did there? So my answer for A is 0.553. What are we noticing about the problems here that we're doing? It's all about the setup. The actual solving, the calculator is going to do all of the heavy lifting for you. The hard part is going to be, what do I get into my calculator? You guys kind of see what I'm talking about? There's not a lot of work to show per se. But that's the trick here. All right. What if we have this one? Again, we're going to sketch the norm or the distribution. Here I've left off the standard deviations because, like, whatever, it doesn't really matter. Just going to bang this through on my calculator. There we go. About 17. Does that feel okay? Same idea. Just I don't have standard normal now, but like whoop-de-doo. All right. Ooh, story problems. Ah! Words. Cartons of juice are such that their volumes are given by the normal distribution 155. 5% of cartons are rejected for containing too little juice. Find the minimum volume to the nearest milliliter that a carton must contain if it is to be accepted. What do I do to start? Draw a picture. Yeah. So I drew this curve. How many of you would have shaded this side, given the phrasing of this question? Well, it's rejecting for too little juice. The probability, the minimum value they're accepted. A lot of us probably would have wanted to shade this side. Is that okay? Yes, it'll be okay. What's the problem though? To get it into your calculator, you're going to have to do the conjugate or the complement. And guess what you get? That piece anyway. So it's fine if you thought to doing it the other way, but you have to do a complement then, and then you end up with what we have here anyway. So we're just looking for the probability that V is less than A is 5%. So I inverse norm that up to about 42 milliliters. What do you guys think there? It's okay? All right. Another example. Sacks of potatoes with mean weight of 5 grams are packed by an automatic loader. In a test, it was found 10% of bags were over 5.2 kilograms. Use the information to find the standard deviation of the potatoes. Oh no. Can I use my calculator if I don't know the standard deviation? Right? Normal CDF and inverse norm CDF both required a standard deviation to use this. Mr. Kulik, what am I going to do? This is why the standard normal distribution is so important. What we're going to do is we're going to figure out the measurement for a standard normal distribution and then convert that using the z-score to this situation. Is everybody okay with that? The reason that's going to work is because I know the mean and standard deviation for the standard normal distribution. They are 0 and 1. All right. So here we go. We're looking for the standard deviation. So the z-score, we have 5.2, that's our measurement, minus 5, that's our mean. So our z-score would be 0.2 over sigma. So if I take this as a standard normal, I convert it using the complement rule so that I can use my calculator from a greater than to a less than. I bang that through on my calculator, I get about 0.128. I can then set that equal to 0.2 over sigma and solve for sigma. This is probably the most difficult kind of problem you'll see in chapter 12. Okay. The key here is that we convert it or we use the standard normal distribution. Okay. And that's it. I want to remind you guys that the chapter 12 homework is Sunday's problem set. So 12.1, 12.2, 12.3 homeworks. Remember, you do get 2 drops though. So if you've done all the homeworks and you have 100% in homework and there's no missings or anything, If you forgot to do this one, you wouldn't be penalized for it grade-wise. The whole problem.
Really?
We will do a test on chapter 12, but when will that happen?
Next semester.
Yes, next semester. I want to point out to you one more thing before you guys run out of here on me. Is I put the in-class examples and the answers all into OneNote. So if you're working on your homeworks, you can check on those. We won't have time to do it today. You are dismissed. Enjoy your lunch. Merry Christmas. We'll see you in 2025.
Wait, Mr. Cooley, so if I have 100 in homework grades right now, I don't have to, like, out of 5?
Yes.
Okay. 'Cause I don't